Thank you, everybody. Welcome to the January 2022 Chemical Consultants Network meeting. I'm Mike Michalczek, the chair of CCN. For those in the audience that don't know, Chemical Consultants Network is a group of chemists and chemical engineers that provides guidance, expertise, and resources to members who are consulting or are interested in consulting. Please mute your mic.
On the umbrella.
We are a topical group of the Philadelphia section of the ACS. We are supported by AICHE. We hold monthly meetings on topics of interest, and for $35 per year, paid members can create a webpage on our website to attract potential clients. This is a great time to sign up. It's the first of the year. Your $35 goes all year, and you can sign up to be a member at chemicalconsultants.org. So tonight's speaker is Jeff Kargel, senior scientist at the Planetary Science Institute. So Jeff is a planetary scientist, a geologist, and a glaciologist. He has experience in a variety of fields. He's the former director of the Global Land and Ice Measurements from Space Consortium that mapped the glaciers, and currently works on Earth glaciers and the geology, geochemistry, and climates of planets and moons in our solar system. His talk tonight is Planetary Climate Change and Extreme Weather. So Jeff, we're recording, by the way. I think Joanne already said that. Yeah. So Jeff, take it away.
Okay. Thanks, Mike and Joanne. And so I presume you can hear me well and you can see the slide just fine. So yeah, I'll be talking about planetary climate change and extreme weather. Just for time constraints, I will leave the extreme weather for a discussion at the end, since we probably all have some personal familiarity with extreme weather in our backyards. And I will talk primarily about climate change on Mars and on Earth, both long-term climate change and recent anthropogenic change. So, and let's see, why is my slide not advancing? Okay, so I guess it's just slow for some reason.
It's slow, yeah, it advanced.
Okay, so I'll be talking about those topics. This is a pretty slide that a picture I took. Some people hear that I'm a planetary scientist and they say, oh, you spend all your time looking through telescopes, don't you? And I say, well, as a kid, I had a 2.5-inch telescope and I spent a lot of time looking through it. And they say, oh, well, you must build and fly spacecraft. And no, I use spacecraft data. So I came into planetary science as a nerdy Apollo era kid. And basically Apollo launched me. So there's the moon down in the lower right. And, through the magic of iPhone, somehow Venus looks brighter than the crescent moon, but who can figure? So when I say launched me in planetary science, I've kind of been all over the neighborhood in solar system studies. So I've studied Venus volcanism and petrology, landing site geology from the Soviet landers back in the 1980s, global composition of Venus, channels and valleys on Venus, weird chemistry due to a dried out ocean, maybe. I've spent a lot of my career looking at Jupiter's satellites, quite a few of them, but especially Io, some people pronounce it EO, E-I-E-I-O. I've looked at volcanism, very high temperature volcanism, sulfur chemistry, and origin as a burnt out former Europa-like world, and Europa, which is an ice-covered ocean moon. And I was the first to point out that the Galileo spacecraft, when it flew by Europa, would be able to pick up a signal of it through the magnetic field, the magnetic induction field, if it was a salty ocean. And I've written on the ocean's chemistry, possible life and metabolic schemes. And Saturn and its moons, especially Tiny and Arizona Width Enceladus, which is another ice-covered ocean moon. It's spewing right as we speak still gas-rich aqueous emissions, forming plumes 50 kilometers, 100 kilometers high, some of it escaping into space. The chemistry of the ocean and icy shell, methane and other clathrate hydrates, the tectonics, and Titan's icy, gassy, aqueous volcanism, liquefied natural gas, methane, ethane solutions, the composition of rainfall and lakes. If you didn't hear, Titan has rainfall and lakes, but it's methane, ethane, nitrogen, and climate change. And Earth, the global composition of our planet, the origin, differentiation, glaciation, mountain hazards and disasters, and climate change. So now about Mars. So Mars was a wet and icy world. Now it's icy, cold, and dry, except there's water, kilometers underground, we believe. There's a host of features that I'm not going to have time to show you. Small gullies, dendritic river valleys. I'll show you some evidence of likely freeze-thaw of glaciers, of permafrost. Groundwater systems, including hot springs. We had a rover, the Spirit rover, visited a hot spring deposit and did a very detailed chemical and mineralogical study of it. Lakes, I'm talking about there were lakes, even oceans, and many, many minerals are vestiges of those water periods. Mars has a thin atmosphere. It's about 1% as dense as Earth's. What passes for heavy cloud cover is shown here, just, these thin, wispy clouds at the Perseverance exploration site in Jezero Crater. You can also see a dust devil. I should also give a call out to Don Davis, my colleague at PSI, who did the processing of this image. And but the typical total atmospheric column abundance of water vapor would make a condensed ice layer about 10 or 20 microns thick on most days, except in the summertime near the sublimating polar caps. This is another Don Davis production. He used Perseverance rover images, stitched them together, and showed a halo around the sun. And I did a measurement. I have no idea if it's valid, given the geometry. Wouldn't you know, I would be the one who did that. I came up with 26 and point some degrees for the radius of the halo, which does not match the 22 degrees for ice crystals. According to somebody who I have in the upper right slide, it may be CO2 ice in this case. Mars does have water ice halos also. My entry into Mars science really was, aside from being a high school kid or recent high school grad and interested in the Viking 1 and 2 landers and orbiters, it was really this paper by Tim Parker and colleagues. He had this boring title with a really exciting idea that there were oceans on Mars. And after several failed attempts to publish it, he deliberately buried the ocean deep in the paper and produced a very boring title so that it could pass peer review. It was about the same time that I was passing some time as a graduate student when I wanted a distraction from my dissertation work. I would leaf through filing cabinets of Viking orbiter photos. Yeah, back in those days, we didn't have digital images, but we had filing cabinet after filing cabinet full of pictures. And I came across this one. It's the rim of a giant impact basin about 1,000 kilometers across, showing part of the rim. Those mountains are quite high, up to 5 kilometers high. And then there's that flat plain at the top of the image with those sinuous what I thought at first were sinuous channels, braided channels, but then I got my ups and downs right, and I realized they were ridges, and my mind went straight away back to an undergraduate field trip that I took in Ohio to an esker, which is a subglacially deposited stream bed, which builds upwards into the ice with sand and gravel and boulders. And then eventually the ice goes away and you're left with a ridge. And I thought, oh my gosh, these look like eskers. They're huge. You know, the system is 300 kilometers long. But I thought, well, if they're eskers, there will be other glacial landforms. And I looked around, and sure enough, these mountains sure do look like they're glacially eroded. I'll get to more about that. Soon we had a paper in Nature on the ancient oceans, ice sheets, and the hydrological cycle on Mars. This was really the first effort to put together a hydrological story for Mars as a global system. And my little piece of this was the austral ice sheet in the southern hemisphere. And Tim Parker's part, he was not an author. We actually had quite a tense relationship, because, you know, professional relationship, because he really wanted there to be, you know, not quite palm trees growing on the beaches, but, you know, our view of it was that it was a really damn cold ocean and maybe iced over most of the time. And I think that's still correct. And so we had this scheme where there would be a transient greenhouse atmosphere triggered fundamentally by volcanism and geothermal heat flow, and it would set into motion a wide range of atmospheric and surface geomorphological responses. At the time, though, we just had really poor quality Viking orbiter images. I mean, poor quality by today's standards, and that was it. You know, we had air pressure measurements, which, you know, gave us some rough idea of elevation changes. The topographic map was like plus or minus 2 kilometers error bars. You know, so we could tell if an 8 kilometer deep canyon was, you know, 6 or 8 or 10 kilometers deep, but we could not see the slopes on surface planes. Finally, a whole flotilla of spacecraft arrived starting in 1998, well, 1997 with the Pathfinder rover. And these images were obtained, and those sinuous ridges that you see, I have them marked bouldery ridges, eskers. You know, you can put a question mark there if you want. Some people still question it. But I had predicted that they would be bouldery, and they sure indeed are bouldery. And the smooth plains in between the eskers, I said, well, I think those are probably lake plains. And you can see the polygons at lower left, and in that little panel, you can see a circular feature in the upper right of that panel. It's an impact crater that is buried with sediment, and the sediment is all cracked up. Probably these are mud desiccation cracks. They could be salt desiccation cracks as well. And so, you know, the hypothesis seemed to pan out. I said if the mountains were glacially eroded, we should see scour features. Indeed, the lower left panel, you see glacial scour. The lower right panel or lower center, again, you see more glacial scour features. And on the right-hand side, you can, in the far upper right, you can see crevasses in glaciers, and you can see one image of flow features and some melt features and erosion features. Here are some more. The lower left is outwash from, I think, melted glaciers, and sculptured bouldery landscape that, you know, might be where a moraine or at least a bouldery surface was run over by a glacier. In the right hand side, you can see more crevasses, and I need to move on faster. You can see more meltwater features. And about the shapes of the mountains, we flew in that 1998 spacecraft, Mars Global Surveyor. We flew a laser altimeter, which finally gave us a real good topographic map. And here's at left is one topographic profile. And there are lots of them across this terrain. And what you'll see is, well, first of all, you can see that the mountains are pretty high, you know, from basin to highest peak, it's over 6 kilometers high, so 20,000 feet of relief. And you can also see that the mountains have a lot of U-shaped valleys and sharp ridges. This is a hallmark of glacial erosion. And you can take any profile, and as long as you dodge the obvious impact craters, which there are not very many here, but dodge obvious impact craters, which also have a bowl shape to them or can have a bowl shape. The U-shaped valleys are diagnostic of alpine glacial erosion. There's no features on Earth that have this kind of large scale U-shaped valleys with and U set in U. Here on the right, you see two famous U-shaped valleys. The top one shows one of these U's shaped within U's. This is where a big glacier was flowing down a valley. This is actually near a mountain pass, flowing off the pass. And then the glacier shrank to a smaller size and cut a deeper U. And then Glacier National Park in lower right. I forgot to point out the upper right is in Scotland. At left are three profiles, actually two profiles and one zoom in, I think. And what you see again, you know, I pointed out that any one of the profiles going in any orientation has this kind of structure, and the bottom shows a zoom in of one of these U-shaped valleys, and there's a parabola fit to it with the dotted line. The axis is slightly off vertical, and you get a really spectacular fit. It's like an ideal parabolic valley. And then Grinnell, lower Lake St. Mary Valley in Glacier National Park is the red profile. The little tiny flaw near the bottom of it is just from a post-glacial stream valley. Again, it's a very beautiful parabolic valley. And you can see that the valley on Mars, it's in the Argyre impact basin, really dwarfs the Glacier National Park feature. I'm going to move on. And so Mars was also a wet world. Here we see an image mosaic, very rugged impact basin topography that is very, very highly degraded. And you'll see all through this area a bunch of channels or valleys. And you know, I wish I had a laser pointer here, but I can point to it with my finger. That won't work. But what in the upper left where it says area of ponding or wetlands, you can faintly see some topographic contours associated with that. And I have one contour dashed with a bold black line. And that's a topographic contour. You see that a lot of the valleys just fade away as it enters this area. There is ponding there. And then it spilled to another channel where a whole series of channels marked with the bold black arrows down to a lower basin. And that has a solid, not dashed line that also marks out a topographic contour. And the white arrow at top center points to one of these valleys where it enters that lake basin. And here's what it looks like at left. It's a delta. It's an ideal bird's foot delta, like the Mississippi River Delta. And you can see I won't belabor the evolution of this, but there's a time sequence of formation of different delta lobes, just like in the Mississippi Delta or other deltas. Here's a little zoom in at the far upper left. You see a zoom in of an oxbow, a cutoff meander loop with what we call scroll bars where the meander migrated. I need to move on. Far left is again the same delta in a color image. Yeah, Mars is not that colorful a planet. It's like red. But there's also white. And what is that white? Well, on the right side is another data set. It's from the CRISM instrument, which is a hyperspectral imaging device. And in this false color image, red is olivine or other iron-bearing silicate sand. Bright blue and white are iron magnesium phyllosilicates, clay minerals. So the white stuff that you see by eye on the left is clay. Clay, they're hydroxylated minerals formed by hydrolysis of minerals like olivine and other minerals. So this is a sign of aqueous alteration of that material. It also explains, I forgot to point out, the bird's foot delta stands as an elevated feature. They're not inset channels, but they're raised. And the thinking is that sand was flowing down the river, and then around the delta was the lake water, and it was muddy, and mud settled. That was phyllosilicate rich mud and fine-grained material, which then later most of it blew away and left the channel beds as elevated features. A lot of deltas on Mars, there are quite a few of them, are elevated. We call it inverted topography. They exist on Earth also. Here's another delta. You can see a valley coming in from the upper left. And again, it's entering into a crater through a breach. And then right in the middle, you see the delta. Well, this is where the Perseverance rover landed. This was its landing site. The idea is that still to be tested, Perseverance has barely begun its mission. It landed like a year ago and almost a year ago, but this is what we think happened. That there was a flow, and then once the river entered the lake, it lost energy and deposited sediment into a delta. And so this shows the planned pathway in the dotted line, and the solid line shows the path so far taken by the Perseverance rover. And so the idea is definitely to explore this delta. Today, Mars is an icy world, so there's no lakes on Mars. There is wet soil in some places. It's really super salty and super acidic soil, and with very low melting temperatures of the eutectic solutions. But for the most part, liquid water is absent from the surface. As I mentioned, it probably exists underneath the ground by some kilometers, but Mars is just so darn cold. In the lower left is a region of the Bering Land Bridge National Preserve in Alaska, and those are called ice wedge polygons formed by freeze-thaw. And then on the right, you see some systems of what we think are ice wedge polygons on Mars. The implication is that freeze-thaw activity occurred there, and maybe not all that long ago. You notice there are no impact craters here, except these are developed inside impact craters, big ones, where there were lakes. And here we see some glaciers. On the left, two main panels are Martian glaciers, and then on right are some terrestrial analog features. And in case you're wondering, it looks awfully dirty. I don't see any bright blue, clean, or white and blue glaciers like I love so much on Earth. Are they really icy? Are they still icy? Well, the answer is yes. At least many of them are still icy. Here, for example, in the upper right, the dashed line shows a transect for a radar observation across a glacial type feature. And the bottom two panels are the radar profiles. And you can see around the mountains, there are these aprons. One of the mountains is blown up on the right and the yellow arrows point to it. And you can see this, there is a surface reflection. There's also a basement reflection, a basal reflection. And this glacier is about, excuse me, about 400 meters thick. It has to be nearly pure ice. It's debris covered. That's why there's a strong surface reflection, but the surface debris is very thin, probably on the order of 0.5 meter. And then it's nearly pure ice. Otherwise, the radar beam, the ice penetrating radar, would not have penetrated through the ice. Mars is also a salty world. Every lander we've had has discovered salts, or at least with the Viking landers, they didn't have the ability to detect salts, but the elemental chemistry suggests that there are salts there. Every lander shows salts. So at the left is a big impact crater. It's about 300 kilometers in diameter with a very complexly disrupted crater floor. There is some layer of sediment that was deposited and then it became destabilized. Probably it was icy and it was definitely salty. The blue patterns are various hydrated minerals. Kieserite is magnesium sulfate .1 H2O. And then there
Jeff, did we lose you? He's talking.
Jeff, we lost you for a short, maybe about 30 seconds there. Let's see if his connection improves. That image looks frozen, but he still shows as here. Okay, we'll get this straightened out.
Sorry about that.
Yeah, Jeff dropped off, so I assume he's going to dial back in, and that'll take a couple minutes.
Yeah, I've already texted him to let him know he dropped off, so.
I don't have any music to play, or I would.
Well, I was very interested in the fact that it was a U-shaped valley, because to me, on Earth, there's two types of valleys that I understand occur. One of them is U-shaped, which is the glacier, and one of them is a V-shaped, which is erosion by void water. And are there other types of valleys besides those?
That's a good question. I'm not really sure. I know the U-shaped valley is indicative of glaciers, but.
Right. Yeah, I think that was his point.
Yeah.
That was Jeff's point. But
Yeah.
I was just wondering if anybody knows of any other types of valleys, because if it's not, it has, to me, a valley should be U-shaped. Otherwise, it's indicative of a flowing water, free flowing water.
Yeah. He's going to be on in a minute. We called Jeff, so.
Yeah, good.
I don't know, Peter, good question. I'm not an expert in valleys, so I don't know.
Silicon Valley is another type, I believe.
Roman, tell a joke.
I don't know any jokes. I'm just know another type of valleys.
Yeah. Jeff wrote a book on Mars, so it's still it's available if you want to purchase it. It's a really good book about
Yeah.
you know, he was one of the first.
I mean, I'm just amazed.
I'm
just amazed of how much water there seems to apparently be on Mars, and you know, it's just amazing. And
Yeah.
it has not. There is still solid. It has not, but it's not evaporated. It has not sublimated. You know,
This was way back in.
What?
Sorry.
Yeah.
Jeff is
I
on his
agree,
way back
Peter.
in.
I think it's interesting because my understanding is Mars and the Earth were very alike. And then something happened to Mars.
Okay, I'm back.
There he is.
Great.
Jeff, you're good.
It's probably connecting.
Just have to get back to share the screen and pick up where he left off.
Okay, can you hear me?
Yes.
Yes. Keep going.
Okay, I think you can hear me and I should be able to hear you. I need to catch up. Can you hear me?
Yeah, you're good, Jeff. Just continue.
Okay, sorry about that. I thought it wasn't going to do this. Okay, so okay, I'll just start here. Okay, the Opportunity rover in 2004. I need to put in some chemistry, so I'll do that here. The Opportunity rover in 2004, it landed with the airbags. You might remember that, and it bounced along something like 22 times and ended up falling into one of the few big, well, not big, a 22-meter diameter impact crater. And there it was. It managed to get out, which was a good thing. But it also had some interesting science right there. But you see this plane that it landed on is cracked up. You can see these polygonal cracks. They're again, probably these ice wedge or maybe salt desiccation polygons. Viewed up close, I think this scene is about half a meter across, as I recall. It's got mud cracks or salt desiccation cracks. And this material turns out to be, this is a very, very false color, exaggerated color. Everything would be red to the eye, but there's less red and more red material. The cracked material is salts. And here's one of the outcrops, one of several, called the Burns Cliff, or the Burns Formation is the geological name. It's the rim of an impact crater, a small one, 120 meters across. And this outcrop was analyzed in detail, mineralogically and elementally. And it turns out that the elemental composition is consistent with, actually pretty much requires it to be mostly salts, magnesium sulfate, sodium chloride, various salts. And my colleague, Giles Marion, and I and other colleagues looked at the chemistry of a whole sequence. I should point out that the outcrop was studied from bottom to top, going all the way with samples taken. And these are those samples. Going down in the graph means going deeper or lower in the stratigraphy. And I just have highlighted in red and green the sulfate and the chloride in red and sulfate in green. And you can see that they vary in opposition to one another, in inverse correlation. You can also see on the far right, the total cations and total anions add up. That sodium is roughly equal to chloride, and calcium plus magnesium is roughly equal to sulfate. And so we think those are the salts. And in fact, those have been positively detected using other instrumentation from orbit. And so if you take just one of these samples, here the Manitoba 2 sample right from the middle of the sequence, and just calculate out what the salt component is, like disregarding the silica and some other stuff that won't form salts at these conditions. And then just do a drying experiment. I mean, a drying numerical experiment using a model, we call it freeze chem, that we developed. And this is a variation. If you add a kilogram of water to a kilogram of this rock, dissolve out the salts, this is what you get. The soluble stuff varies. Again, I have highlighted the chloride, chlorine, and sulfate, and you can see them co-varying. And what this means is that there were magnesium, calcium, sodium sulfates, and sodium chloride. This material would be precipitating salts really in the high 260s Kelvin. We did our drying modeling at 270 Kelvin, which is life-friendly for known psychrophile and halotolerant microbes. I'm going to move on. The bromine is interesting, but okay. So Mars has had serious climate gyrations, formation and freezing and evaporation of oceans, deposition of ocean-sized salt deposits, coming and going of continental scale ice sheets, widespread melting of mountain glaciers and permafrost ice, sediment rhythms of many scales and types, formation and changes of polar caps, smaller glacial epochs coming and going, long periods like now of hyper-arid, dusty, and cryogenic conditions. Humans are not yet at fault for messing with Martian climate gyrations. There are many indicators of a former warmer, wetter periods contrasted with current conditions, demonstrating that epochal climate change on Mars has occurred, and there have been milder oscillations of climate also. Solar luminosity is one of the big drivers of it. But if you just went on the basis of solar luminosity, you would say that early in solar system history, it should have been frozen even more than it is now. And it should have just gotten warmer and wetter consistently, but it hasn't. And it means that there's something else going on that is balancing out the solar luminosity changes. And that something is greenhouse gases, we think. Episodic emissions of greenhouse gases into the atmosphere. A former warmer, wetter Martian climate contrasted with current conditions demonstrates epochal climate change, with drivers including also solar oscillations like the 11-year solar sunspot cycle. It affects climate on Earth, and it affects Martian climate too, but I'll discuss those variations later. Drivers also include orbital and spin oscillations. As with Earth, the periods are different because the orbital parameters and spin characteristics of Mars are different. But the axial tilt, which of course gives the Earth our seasons, also gives Mars its seasons. And it has really wild, it doesn't have a big moon that kind of anchors down the obliquity to a narrow range of values. It has really incredibly wide ranges of obliquity changes from about nearly 0 degrees, meaning there would be no seasons, to up to 60 degrees actually at times. So that the pole faces more towards the sun during the summer than otherwise. And then there are eccentricity changes. And we see the effects of this in the Martian polar caps. Drivers also include geological activity like volcanism. This volcano would span the width of Arizona. It's 21,000 meters high, 69,000 feet. Tectonics, such as the opening up of Valles Marineris, it's over 3,000 kilometers long and up to 8,000, even more meters deep. Other drivers of geological activity include giant impacts, geothermal variations, ocean formation and dissipation. All of these things can release greenhouse gases. Ice sheet formation and dissipation, crustal weathering, such as hydrolysis and carbonate formation. It can suck up gases. albedo reflectance changes related to dust and ice deposits or removal, dust storm activity, maybe biological activity that can be involved in methanogenesis or other cycles. These processes, however, happen slowly, except for giant impacts and dust storm activity. Greenhouse gases, gas storage and release mechanisms in one part of the system can compensate for changes in other parts. And so in this way, there have been warm, wet epochs really throughout Martian history. However, Mars's history indicates that the regulation has been very poor. It's not like the Earth, where liquid water is pretty much always present to some degree or another, even during the snowball Earth period 700 million years ago. I'm going to, well, no, I should talk about stable states. It looks like, to me, like the most stable state is cold and dry. That's where Mars wants to be. But geology keeps interfering and episodically dumps greenhouse gases into the atmosphere. Carbon dioxide especially, we think possibly methane also, but the climate reverts, it keeps revert to its cold and dry state until the next perturbation. Now Venus, this is my only Venus slide. Venus likely once had an ocean's worth of water. Excuse me. That's from the deuterium to hydrogen ratio of the atmosphere, which is the solar system's highest. We think that that's an indication that there is a huge amount of water loss. There are alternative explanations involving cometary impacts, but the same thing happens to Earth and we don't have the same signal. It really looks like it was an ocean. So the oceans must have evaporated into a steam atmosphere. Then water was photolyzed, hydrogen escaped, and oxygen reacted with the crust and mantle, and it became the Venus that we know. The same climate crisis will eventually happen to Earth. I think about 2 billion years from now, but there are things that make me think not anthropogenic warming. Humans, I do not believe, are going to make Earth become like Venus, but it could happen much sooner. But we're still talking hundreds of millions of years from now. Earth is also believed to have two current stable states. One is roughly like Earth now, with oscillations, around, between ice ages and what we call hot houses, but water's always present. We always have oceans. And a steam atmosphere, which would then photolyze and do the same thing that happened to Venus. These are both stable states, but you have to get there first. There's a kinetic barrier, and we don't know exactly what those barriers are. Rising solar luminosity probably helped Venus, but it was probably something else also, a spasm of geological activity, especially volcanism, that seems to have done it. But it's sort of a mystery. We've got 4 missions, we the world. The US has 2, Europe has 1, and Russia has 1, aiming for Venus over the next decade. So we'll learn a lot more. So humans are not likely to tip Earth's condition into a steam atmosphere and then a Venus-like state. Nature has done far worse in the distant past. I'll move quickly. Humans need to be concerned about the whole lifeboat, including humans. Scientists are learning on the job about climate change and tipping points with observations and modeling. Society learns by disasters and insurance and mitigation and adaptation costs. We're performing an uncontrolled experiment on our climate and life support system. We don't know what all the knobs and buttons do. This is fundamentally the problem with the rising CO2 and rising methane. So some people say things like something else is causing the increases, right? It can't be us humans and our industrial civilization. Well, this is what carbon dioxide and in the bottom panel, methane have been doing. The only silver lining here that I see is that since the 1990s, the increase in methane has been slower than it was in the 1990s and 80s and 70s. It's still shooting upward, but apparently regulations have clamped down on leakage from pipelines and wells to some extent. But still, you see these greenhouse gases going up, up, up. And look at the values, over about 417 parts per million for carbon dioxide. We'll come back to that soon. Here are ice cores showing in green methane variations over the last 800,000 years, and carbon dioxide in red, and then a measure and a proxy for temperature in black, which is from deuterium to hydrogen in the ice. And you see that methane and carbon dioxide and temperature are roughly in lockstep. When you zoom in, you can see that there are lagging CO2, by a few thousand years. That's because of the time required for ice sheets to build up and for ice sheets to dissipate once you've triggered a temperature change. And it's been known, the effects of these CO2 at least, has been known since the 1890s. And it was predicted that the Earth would undergo global warming due to industrialization. In the 1890s, however, the time scale was wrong. They thought it would take 300 years to get to where we are now, or where we were even 2 decades ago. But the process is known. It's very complicated in detail, but the most fundamental physics is just that you're messing with the black body. The outgoing heat of the Earth is not the black body temperature of the Earth's solid surface, because you have these heat trapping gases here showing carbon dioxide, ozone, and methane and water vapor. And if you're blocking the heat escaping, you have to raise the Earth's surface temperature in order to get a balance of incoming and outgoing energy. I will move on. So what's causing all of it? People say volcanism, they say this, that, and the other. Well, it's all of the things you've heard about. It's the sun, it's volcanism, it's it's orbital changes, and it's greenhouse gases. But the elephant in the room is greenhouse gases. And in fact, when you put all these forcings together, it very well explains the Earth's instrumental record of temperatures. But I won't go into this. Will be online for you to look at your leisure. I need to move on. I'll just do a qualitative thing right here. These are fossils from John Day fossil beds in Oregon, Central Oregon, and a wall mural at the National Monument. And the fossil assemblage shows a subtropical climate 44 to 40 million years ago. And with uncontrolled greenhouse gas emissions, business as usual, before the beginning of the 22nd century, we will be at these conditions. If we have, excuse me, excuse me, sorry about that. It's not COVID, it's just my chronic cough when I start talking. This has a log scale, so you can see 1 is 10 years ago, 2 is 100 years ago, 7 is 10 million years ago, et cetera. Logarithms. So it's not a linear time scale. This shows the global surface temperature, global average surface temperature. And we are now, at the last several years, we have exceeded the global temperature of the Earth during the entire period of human civilization, including the medieval warm period and other natural changes. We have outstripped nature. In fact, you have to go back 120,000 years to find a year that is as warm as, for example, last year. And if we have a low emission scenario, by the year 2100, we'll have to go back to the time of Lucy. Lucy would have experienced a climate similar to what we will have on Earth in 2100. Lucy, the Australopithecine, Australopithecus. And business as usual would have us having a climate similar to the John Day fossil beds, with Central Oregon having a subtropical climate and Panama being utterly uninhabitable, as well as, a large part of the Earth, certainly Arizona. So should we terraform Mars? I say forget it. Let's just avoid lunaforming the Earth. If continents aggregate near the poles in the future like they did 700 million years ago, we could have a third stable state, which would be a snowball Earth. However, eventually a Venus-like state is guaranteed. Under a red giant sun, the Earth's crust and mantle will become a magma ocean. We don't need to worry about that right now. I don't lose sleep over it, but it's going to happen for sure. And I guess this version of it, I do not have my thank you note, so I'll just end the talk and say thank you very much.
Thank you, Jeff.
Okay.
So if anybody wants to ask any questions, please add them to the chat. So Jeff, I just want to ask a quick question. I saw Nova once on Mars, and they talked about one of the reasons that Mars lost its atmosphere was the magnetic field. The core cooled, and it lost its magnetic field. Is there any indication that Earth would have a similar issue with that?
The core of the Earth is probably going to be liquid for a lot longer, but we do have a solid core that's forming. And one of the reasons we have a magnetic field, this is one of the hypotheses, but it's probably correct, is that the core is cooling. And what's happening is that iron is crystallizing and is sinking down to form the solid core. And that is releasing heat, so it's cooling from the surface, but then it's releasing heat deeper down, and that's causing convection. And so the Earth's core is solidifying, and it's going to solidify. I don't know what time scale it will solidify on. I don't know if it will solidify in time for that to happen. We don't need to worry about it now. There have been many, many, many episodes where the Earth's magnetic field has almost disappeared when it undergoes magnetic reversals. And, it would probably be problematic for civilization if a reversal happened now, and they can happen quickly. And there is a hypothesis out there based on observations that we are due for a reversal, and the beginnings of the reversal process are already happening. This is something that could happen within our lifetimes, but the Earth's magnetic field is really complicated. It's not a straight up dipole. It has quadrupolar and octopolar components. And so, we might have auroras at weird locations, but we'll still have magnetic shielding to some extent, because if it wasn't the case, the hundreds of magnetic field reversals that have happened in the geologic past would have rendered us really bad. But Mars is a different story. It looks like it lost its magnetic field completely, except for the permanent magnetism that was imbued in some of the ferroelectric materials composing the crust, which is a very weak magnetic field. And yeah, that's one of the major contributors to Mars losing its atmosphere. Scientists go around and around and around about, how effective it is. And I think it's probably very effective, but who knows?
Yep. So we have a couple questions on the chat. One is from Peter Mlanik. Why does the ice on Mars not sublimate?
Well, it does sublimate. It does sublimate. That's a good question. If you got a solid and it's at any temperature, there is a vapor pressure. And it's just very darn low when the temperatures are as cold as they are. But it does sublimate. And I mentioned the 10 to 20 precipitable microns of water in the atmosphere. That's because ice is sublimating. And it's also condensing. There's a water cycle on Mars. And ice moves from pole to pole. And also ice is being found at very low latitudes these days. That when I was in grad school, the physicists said, geophysicists, us geologists, we always blame the geophysicists if things don't go right. The geophysicists said, oh, there's no ice. Equator words of about 30 to 40 degrees latitude. Well, we're finding ice. And there are just ways to keep it from sublimating so fast and to hold it for some time. And then you've got this persnickety bit of geological activity that keeps putting water from the interior onto the surface. And so that refreshes the water. And so Mars is in a constant state, I would say right now in a slow state of reestablishing equilibrium, and then geology hits it again and destabilizes it, and you get warm wet epochs, and the clock is reset on getting rid of the ice near the equator. During high obliquity periods also, the polar ices can sublimate and get deposited near the equator.
Yep.
So it gets complicated.
Yep.
So my question was, yeah, sorry. My question was essentially, does the water evaporate into the atmosphere, and does that water then the water molecules leave the atmosphere because they are so light, and the gravity is so low on Mars?
Yeah, that's a very good question. Actually, a couple of them. So or points. So yeah, the ice sublimates. It goes into the atmosphere,
right,
and most of that water on any given summer. Excuse me. The ice will sublimate from where you have ice near the surface, goes into the atmosphere, cycles to somewhere else, to some cold spot. In the winter time, it makes frost. It probably snows out. It certainly snows out with carbon dioxide ice, and then gets left behind as the carbon dioxide ice sublimates. And so there's a water cycle on Mars for sure. But water itself will not escape from Mars directly, but it goes into the upper atmosphere, and even the lower atmosphere, and ultraviolet rays and cosmic rays hit it and ionize it. Not the water molecule, breaks it apart, fissions it, and so you get hydrogen and oxygen. And the hydrogen blows off. The oxygen is left there, and it reacts with the surface. And this is probably a large part of the reason why Mars is red. There's so much rusted iron. So you can do remote sensing with your eyeball and look at some of the geological and geochemical hydrogeological processes with your eyeball in the evening or the morning when Mars is visible. Not right now in North America, anywhere in the it'll have to wait till, for evening views, it'll have to wait, I think, a month or two. And so, yeah, your eyeball is a good remote sensing device, not quantitative, but fun. Yeah.
So we have a couple more questions, Jeff. So Keith Wing asked, Jeff, please comment on polar ice sheets and caps melting and sliding into oceans, on global jet streams and climate and ocean levels, also exposure of permafrost leading to methane production.
Okay, so for part 2 of my talk, okay, yeah, I'm glad that Keith mentioned that. Yeah, so the CO2 in the atmosphere of Earth is now 417 parts per million. Those jiggly, are you still able to see my slides? No.
We can see them. Yep.
Oh, okay. So, okay, those jiggly up and downs for the ice ages and interglacials, you'll see CO2, the red curve, going up to 280, 290, 300 parts per million. We're at 417 parts per million. We're also at 1900 parts per million in methane. We're way off the charts. The ice sheets are not going to survive. Probably I assume that some of the high elevation mountains are going to retain ice, maybe big ice caps even, but most of the ice sheets are going into the ocean. We're watching them go right now. When glaciologists talk about them sliding into the ocean, it's not like people, lay people saying, oh, the San Andreas Fault, California sliding into the ocean. Well, yeah, there are some landslides that sometimes dump a few acres of land into the ocean, and eventually Southern California and Baja will end up in Alaska, but we're not going to see California just suddenly split off. But we are watching real time Greenland and parts of Antarctica sliding into the ocean. That's happening. And it's not going to stop. It's going to accelerate. Now, this doesn't mean that the Greenland ice sheet and the West Antarctic ice sheet, which is the most vulnerable part, are going to just be in the oceans, in our lifetimes. This is a multi-millennium long process. But, that's under normal conditions, under normal natural conditions. Our greenhouse gases are so far out of line, so far out that, I would think that there's going to be a much faster than natural process, but we're still talking a couple millennia for it to go to completion for the Greenland ice sheet and the West Antarctic ice sheet. That still leaves a big mass of ice in the East Antarctic ice sheet, and it will probably mainly remain stable through all this unless we have uncontrolled release of greenhouse gases. So far, I don't really see evidence that we're getting a handle on greenhouse gases. I don't see that. Maybe methane is not going up exponentially anymore, but it's still rising. I'm fairly pessimistic that we're going to meet the low emission scenario. And by the way, that low emission scenario that I showed you, that was based on the previous IPCC report. Low emission scenario now has been reduced. And the reason is because we realize what a pickle we're in. We're in deep, deep trouble. And this is this generation trouble. We see it in the extreme weather. And actually, nobody predicted the kinds of extreme weather. Yeah, there were generalized predictions of, it gets hotter and, some places get drier, you'll have more forest fires. But nobody predicted the conflagrations that are occurring on one continent after another. Nobody predicted, I'm going back 30 years, that Category 5 hurricanes would be anywhere near as common as they are now. Nobody predicted that lightning and the convective storms that they represent would be so hugely increased as has actually been the case. It has to be that there are tipping points, non-linearities in the response of our very dynamic atmosphere to 1.2 degrees of warming. So what is another 0.8 of a degree of warming going to do in a low emission scenario? Now the IPCC is talking about we have to keep it to 1.5 degrees. Well, I'm really sad to say that's hopeless. We're not going to do 1.5 degrees. If we stopped all emissions today, we're going to still coast up in warming because the oceans have not yet come up to equilibrium with our present atmosphere. We are in deep trouble.
We have a couple more questions because we're kind of way over our time. So we'll take one more question, and anybody else who has a follow-up, please contact Jeff. I think his contact information is available if anybody wants to talk to him offline. So the last question is from Alex Augustine is, do you consider carbon capture and sequestration to be a viable technique to offset reduce emissions for the midterm?
Okay, so two important points. First, I am a supporter of carbon capture technology development and testing. Like just in case things are even suckier than I think they are. Okay, then we need to try to pull a rabbit out of the hat. But if we rely on carbon capture technology and say, well, we can just keep doing what we've been doing, business as usual, it becomes a red herring because there are so many ways that what we think, especially if we want to capture carbon on the seafloor as clathrate hydrate, carbon dioxide clathrate hydrate, that is probably not stable. The ocean currents are changing. And what is nice cold temperatures now likely will not be in the future, as the amount of, it's just an unstable place to put it. It's like storing nuclear waste near an earthquake fault zone. You might say, well, our model says it's stable, and it's like, so I'm in favor of the research. I'm in favor of demonstration projects. Definitely our policy should not be dependent on this still almost mythical carbon capture technology, especially capturing carbon dioxide that's already in the atmosphere. Maybe it's possibly feasible at the emission points, but I'm very dubious about that as well. We need to change our technology of energy production. We need to change our transportation. We need to be investing heavily. I mean, when we're having global disaster damages that are pushing towards $1 trillion annually, and plus, all the associated medical costs of, just pollution, nothing to do with climate, but and all the military costs of defending sea lanes and all this stuff. We've got to get off fossil fuels. We have to do it, and we have to do it quickly. I don't think we need to do it in an absolutely knee-jerk way. We have to have a rational plan for doing it, but we have to do it.
So I think we're really over. So I think if anybody wants to follow up with Jeff, I believe his email is available. If not, please contact me, Mike Michalczak, the chair of CCN, and I can provide it if you want to talk to Jeff offline. But thank you very much, Jeff, for a great talk, and we really appreciate it. Thanks.
Okay, thank you very much. Have a good evening or wherever you are. It could be morning for some of you for all, or midnight. Go to
Thank you
sleep.
very much. CCN will have our next talk in February, so look to our website for we'll be doing a joint talk with Philadelphia ACS Young Chemist Committee. So
Okay,
have a good evening, everybody. Thank you.
And I'll join with the $35.
Oh, thank you, Jeff.
Sure.
Got a
Okay.
member.
Okay. Yes.
Thanks a
Okay.
lot.
Yeah. Take care.
Take care. Thank you, everybody. Thank you.
Thank you.